So good morning, students. Good morning, everyone. Last class, you see that channel coding techniques. So channel coding techniques are the methods to detect an errors and correct an errors at the receiving end of the communication system. Detect an errors and correct an errors at the receiving end of the communication system. So it is come under the process of forward error correction method. Forward error correction method. In the forward error correction method, so there is an ability to detect and correct an errors, that ability parameter known as reliability of the information. Reliability of the information. Offer reliable at the received data. Okay. So that channel coding techniques already you know why they go for coding techniques. So if you go for the coding techniques, the performance of the system improves. So performance of the system depends on the probability of bit error and energy for bit by noise prospect density. Energy for bit by noise prospect density. So for that, Shannon's Hartley given that there is a relation between channel capacity and signal bandwidth and signal quality. So that is C is equal to B log 1 plus S by N. C is equal to B log 1 plus S by N. So that is the channel capacity and the rate of information of the source. So how the channel capacity capable to transfer the information from the source to destination. Okay. So here channel capacity also depends on the parameter of mutual information. The mutual information is nothing but information transfer. The measure of information transfer is nothing but the mutual information. Okay. So in that already you see there's some how the channel capacity tends to infinity. What is the optimum probability of bit error, or S by eta B. So that is minus 1.6 dB. So that is the limit of Shannon, limit of the Shannon. So based on that limit, you can divide the entire system, reliable system and non-reliable system, R less than equal to C condition, R greater than equal to C condition. So based on R equal to C condition, at R equal to C condition, it should be minus 1.6 dB. That is known as the Shannon limit. Minus 1.6 dB is the Shannon limit. So in that Shannon limit, R less than equal to C condition, R greater than equal to C condition separated. So, where is R is information rate, C the channel capacity. Is it not? So R less than equal to C condition means that is the realizable system. Realizable system. R greater than equal to C condition means not realizable system. That is over the channel limit. That is R less than equal to C condition. There should be a any system can be realizable. So R greater than C condition, not realizable system. That is the discrimination given by the Shannon. Discrimination given by the Shannon. So here it is. You can see that graph here. So the graph is if the channel capacity tends to infinity, that EB by N naught, S by eta B, that is the probability of bit error. Parameter S by eta B is the probability of bit error, or it is equality of the information. Quality of the information. So that is minus 1.6 dB the limit. So minus 1.6 dB the limit. So that R less than equal to C condition can realize any system, that is communication system. Okay. So and one more parameter is to know that the trade-off between error performance versus bandwidth can improve the error performance when your system is adapted by coding techniques. If the system is adapted by coding techniques, then only error performance going to be increases. So if the error performance going to increases, what happens? The bandwidth also increases. So bandwidth increasing is one of the disadvantage in the communication also. But even though it is disadvantage, you can go for the error performance only, then you can compensate some bandwidth also. So that's why there is a here the two parameters. So error performance and the bandwidth. These two parameters are contradict. So that is, if you want to know that improve the error performance, bandwidth somewhat be increases. But bandwidth increasing is the one of the limitation also. No, now you can set some bandwidth and you can set for some parameter the error performance. So that's why. So if you go for error performance increasing, so then you can adapt coding techniques. So for the coding techniques, adapting means adding the parity bits to the system. Adding the parity bits to the system. Parity bit doesn't have any information. Once again, I tell parity bit doesn't have any information. Parity bit is meant for error detection correction process only. Parity bit is meant for error detection correction process only. So that's why uh, uh, if the parity bits are added, bandwidth absolutely going to be increases. So that's why you can go for error performance versus bandwidth on other parameter. So in the previous class, see that one graph here, that is 10 to the power minus 2 and 8 in the EB band value, that is the A point. So if the solid line is uncoded and dotted line the coded. If the A is the point there, uncoded, there is no coding techniques used in the system, then probability bit rate 10 to the minus 2 and EB band is 8. So that's why the customer complains that voice quality is not clear. So please be improve voice quality at least 10 to the power minus 4. Then what to do? So A to B has to be set point at solid line. At B, what is the EB band value? Somewhat increases. So I would not, I'm not increase the EB band value. So please set the EB band value at 8 only and improve my voice quality. Then can adapt now the coding techniques. That's why the C point is located here. The C point is located means system is designed at 10 to the power minus 4 and EB band value 8. So that is possible when the coding techniques is used in the system. So now one more point is if the power versus bandwidth. Power versus bandwidth. So the power versus bandwidth means if the system is designed without coding techniques at D. So now the error performance is very good. That is 10 to the power minus 6. But EB band value is somewhat large. That is the yielding point. EB band value is somewhat large. Now that customer complains that so my EB band value reduces, not reduce the probability bit error. So retain the probability bit error at 10^-6 and EB band value has to be reduces. Then what to do is, so the E point is located here. The E point is nothing but the error coding techniques is imported on the system. So that's why E point is, so at 9 10 to the power minus 6 is parameter of the probability bit error. So that is wherever the coding techniques are used, bandwidth also increases because of the parity bits are added there. So that is error power versus bandwidth is another second parameter. And third one is capacity versus bandwidth. So when that increases, capacity unit increases. Yep. And also that used in CDMA techniques, code division multiple access techniques, can adapt more number of users to the system. So that is for cellular mobile communications only. So because of the capacity going to increases. Okay. Now the channel coding techniques are two methods. One is waveform coding, another one is structured coding. Channel techniques are two methods. One is waveform coding, another one is structured coding. The waveform coding is you can design a better waveform for the existing waveform. So you can give the waveform that is designed to better waveform. So here one more point here it is, you can give the waveforms. Those waveforms are existing waveforms. So those waveforms are turned into the better waveforms by using waveform coding. Turn into the better waveform by using waveform coding. Here it is one example. It is the data, binary data is 0 and 1. Binary data is 0 and 1. 0 is one signal and 1 is one signal. That will be an example. So there are two signals, logic 0, logic 1. For the two signals, the code word matrix has to be converted. The code word matrix has to be converted. So 0, 0, 0, 1. It is the better one than 0, 1. 0, 1 is the data. For that 0, 0, 0, 1 is another code word. So that instead of 0, 1, you can transmit 0, 0, 0, 1. That is the better waveform. Better waveform. That is the waveform coding. That is H1 is 0, 0, 0, 1. That is uh, uh, the representation of 0, 1. So and so 0, 1 is the two bits are two signals. Suppose bits are 2 to the power of 2. 4 signals are there. What are the signals? 0, 0, 0, 1, 1, 0, 0, 1, 1. Now that waveform coding is converted them into H2. The H2 is equal to, you can observe one point here, it is H1, 0, 0, first row, 0, 1, second row. Is it not? 0, 0, 0, 1. That means 0, 0, 0, 1. So 1 is the uh, um, complex one of the 0. That is inverted one. But 0, inverted 1. So that's why 0, 0, 0, 1. Now H2 is equal to designed as H1, H1, first row, H1, H1 bar in the second row. H1, H1 is the first row, H1, H1 bar is the second row. Likewise, you can arrange any type of waveform coding based on the number of bits are used to the signal. Number of bits are used to the signal. If suppose number of bits are 3, how many signals are there? If the number of bits are 3, how many signals are there? There are 2 to the power of 3, 8 signals are there. What are those? 0, 0, 0, 0, 0, 1, 0, 1, 0, likewise, up to 1, 1, 1. So what is the code matrix? That is H3. H3 is equal to H2, 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 and H2 bar. The first row is H2 and H2. Second row is H2 and H2 bar. So likewise, that's why the k number of bits are used. H of k is equal to H of k minus 1, previous one, and H of k minus 1, H of k minus 1, H of k minus 1 bar, H of k minus 1. So here, that is, you can design a waveform, the better waveform. So better waveform, why you can use the better waveform? Better waveform meant for you can withstand the noise in the channel. In order to withstand the noise in the channel, you can design a better waveform. The better waveform is this is code word matrix here it is. So that is in the form of waveform coding. Waveform coding. So here one definition is observed here, that is cross correlation between the number of bits. Cross correlation between the number of bits. Okay. So that is received data and transmitted data. Received data is a better waveform. Transmitted data is the waveform. So where the better waveform conversion process takes place, so at the coding process only. At the coding process, conversion takes place. That is, conversion is the waveform to better waveform. Now you can correlate the better waveform to waveform now. So that is very essential. So at the end of the communication, that is at the receiving end, you can identify which data is transmitted. So that is one of the important parameters. It is in order to identify that the correlation process is one of the important parameters. So like there are two types of correlations are there in the communications. One of the correlation is autocorrelation, another one is cross correlation. So autocorrelation is the correlation which is the same signal, delayed signal. Same signal, delayed signal is the autocorrelation. The same signal, delayed signal is the autocorrelation. The signal is x of t, like an example. Signal is x of t. If the signal is the same x of t delayed by the some time, suppose uh, 50 seconds or 20 seconds like this. So that is same signal and delayed signal. So the signal is transmitted to the channel. The received end, if it is the delayed one, to the delayed one. How can correlation between two signals, the same signal, delayed signal, same signal, delayed signal. So that is known as autocorrelation. The cross correlation is two different signals. Two different signals are correlated here. So in that one, in the digital domain, number of bits are transmitted. No? Number of bits are transmitted and receive the number of bits. So for that, we can evaluate the cross correlation process. It is Zij, the parameter of the cross correlation. Zij is equal to number of bits having the same value minus number of bits having the different value by total number of bits. The code word. What is the code word? Code word is nothing but the better waveform. The waveform code. The better waveform. That is that one number of bits having the same value minus number of bits in the different value by total number of bits. That is the correlation. So this can be computed by changing every zero of both code words into one and divide the uh, inner product of the two bipolar code words vectors by the code word length. According to the definition, the cross correlation between the any two different code words turn out to be zero. So, implying the orthogonality among the code words and their corresponding signal waveform. On the other hand, the biorthogonal signals can be regarded as converting two bits of data and generally k bits of data in the following way. So there are orthogonal signals and biorthogonal signals are there. Orthogonal signal means same signal but angle difference. Orthogonal signals. You can see that in the waveform coding, the 01 is data, 0001 is the 4 bits are 2 rows are arranged. That is the code word. The 2 bits are there. What is the row length? 4 bits are there. Now 0000, 0101, 0011, 011, 0. So what about H3? The row bits are 8. Now the row bits are 8. Now the extra bits are meant for the parity bits. That is, those increase the bandwidth. Increase the bandwidth. Now the biorthogonal codes are H and H1 bar. H1 is the same. The 2 bits are there. 2 bits are there. How many signals are there? The 2 bits are there. 4 signals are there. 0001, 10, 11. For that, what is biorthogonal code word? B is equal to H and H1 bar. That the vertical position can arrange H and H1 bar. If you now the B of K, biorthogonal stands for B of K minus 1, B of K minus 1 bar. Likewise, since the size of the matrix is reduced in the biorthogonal, size of the matrix is reduced in the biorthogonal. Okay. Now, enter into the another concept of the channel coding. There are three types of channel coding techniques you have in our curriculum. So before that, since the number of columns of the code word matrix is the number of bits per symbol, the number of bits spent for transmission with pi-orthogonal signals is a half of the orthogonal signals and the required channel bandwidth is to be reduces. Is it not? So in compare with orthogonal bi-orthogonal signals, bi-orthogonal signals bandwidth is half of the reduces than the orthogonal signals. Is it not? Because of the arrangement of the bi-orthogonal code word is H1 below that H1 bar, one row H1 below that H1 bar, or H2 and H2 bar likewise. Okay. You have three types of channel coding techniques. One is linear block codes, another one is cyclic codes, another one is convolutional codes. So linear block codes. So students, please be visualize the structured waveform coding. That is, design the better waveform for transmission only. Design the better waveform for transmission only. The better waveform is nothing but code word matrix. Better waveform is nothing but the code word matrix. So at the receiving end, what to do? Decoding process has to be done. Then only receive the signal. Okay. So after encoding, before decoding, that signal is a coded signal. After encoding and before decoding, the signal is coded signal. So now the parity bits are added. The parity bits are added in the communication system. That is the coding technique. That is coding technique. So in the waveform coding, the structure is designed as H1, H1, H2, H3, H4. The orthogonal by orthogonal is H1, B1, B2, likewise. Okay. So wherever you are design the system, that should be a adding of the parity bits. That should be the adding of the parity bits. Okay. So now the linear block codes. Linear block codes. So linear block codes is the coding techniques. So which is structured coding. Structured coding. In the structured coding, you design the better waveform, that is U. U is equal to M into G. Please note that the formula U is equal to M into G, where U is the structured code word and small m is the number of message bits, message vectors. M is number of message vectors. The vector means suppose k is equal to there are 2 to the power of 2, 4 vectors are there. So vector means a signal. Vector means a signal. 2 to the power of 2, 4 signals are there. The signals are 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now the m number of factors are there. That is the message implication. And G is the generator matrix. G is the generator matrix. Now you can see that linear block code is the linear block code. A number of message vectors are there. So n number of code word vectors are there. Message vectors are k number of message vectors, and n number of code word vectors. So absolutely code word vectors are greater than message vectors. So that principle is involved. So you have mapping of n to k, mapping of n to k, where k is message vectors, n is code word vectors. So now the block code is the mapping of n to k or k to n. So based on the uh, matrix mapping, based on the matrix mapping. So that is follows superposition theorem to map k to n, to map k to n. K is the message vectors and n is the code word vectors. So certainly k less than n, always n is greater because of the code word vector is greater. So code word vector is greater than message vector, n greater than k. So how the n greater than k? So the n added by the parity bits, n added by the parity bits. Now that the representation of the linear block code is n comma k. The representation of the linear block code is n comma k. N stands for the code word vectors, k stands for the message vectors, n comma k. So there is 2 to the power of k message vectors, 2 to the power of n code word vectors. Code word vectors means after encoding. After encoding, those code word vectors meant for transmitting through a channel. Meant for transmitting through a channel. So you can represent linear block code by n comma k. Can represent uh, linear block code by n comma k. N represent code word, k represent message word. Okay. Now there is n greater than k. N greater than k principle is involved. So here it is. A block code is said to be linear. A block code is said to be linear if the modulo to sum or difference of any two code words is the block code in the block code is the another code word vector. Another code word vector. So that is, if you design the two code words, if you design the two code words, that is n. You design the two code words, that is n. If the sum and difference of those two code words, sum and difference of the those two code words, then the resultant vector also is the one of the code word vector. The resultant vector also the one of the code word vector. That is the linearity property. Linear property. It obeys the modulo 2 of any two vectors. Any two vectors. The resultant vector should be the code word vector. That is the modulo 2. That is the linear property of the block codes. That's why it is the linear block codes. Linear block codes. Okay. N comma k. N is the code word vector. K is the message vector. So, students, please be this topics. Okay. Linear block code is n comma k. N represents code word vector. K represents message vectors. Okay. So there is n minus k are the parity bits. N minus k are the parity bits. N minus k are the parity bits. N is code word vector. K is message vector. Where n minus k is called parity bits. Suppose n is called 7, k is called 3. N is called 3. N is called 7 means 3. So, but how many vectors are given as input? 7 comma 3 code. I meant to say 7 comma 3 code. For the 7 comma 3 code, 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma 3 code. 2 to the power of 3 is 7 comma going to be transmitted at the end of the that is the encoding technique involved to convert 8 vectors into 128 vectors. So the 128 vectors, 8 are the valid code ones because of only the message vectors are 8 only. That's why the 8 are the valid code words. The remaining vectors are not valid code words. So that is the you can identify how many valid code words are there by the decoding process. Okay. Later we can go for the decoding process. Go for techniques by using linear block codes. So linear block code defined as n comma k vector k is in sequence. So there are minus k is equal to p. It is n is equal to 7, k is equal to 3. What is p value? It is 4. Because 7 minus 3 is equal to 4 now. Now, if it is 4, how many parity vectors are there? Put the power of 4. 16 parity vectors are there. Okay. Now, here n, k, and p are the three. Okay. N is the forward vector, K is the missile vector, P is the back vectors. Now, the structure of the linear block code is U is the code over is equal to M into G. The structure of the linear code is U is equal to M into G. M represents K message vectors. That is M represents K message vectors. U represents N code words. U represents N code words. And now you can design U is equal to M into G. You can design U is equal to M into G. M is the vectors. Now the G is the generator polynomial. You can multiply M with G, then generate U value. U is nothing but N code words. U is equal to N number of code words. M is equal to K number of vectors. Okay. Now the G is the generator polynomial. G is generated. Now entire generator matrix. Okay. So this what the statement here is. Block code is mapping of k bits message vectors into m bit code over vector by using an n comma k block code, which consisting of 2 to the power of k codes of length n. So a block code is said to be a linear if the modulo to sum or difference of any two code words into the block code is another code word belonging to the linear block code. The linear block code is represented by k into n generator matrix. The size of the generator matrix is k into n. Size of the generator matrix is k into n. So k is number of message vector, n is number of code word vectors. So k into n. The size of the generator matrix is k into n, which is modulo to p multiplied by k bit message symbol vector k to yield an n bit code over vector. Now the u is equal to n into g. U is equal to n into g. U is equal to n into g. Accordingly, the encoder and decoder in the linear block code scheme use matrix multiplications, which are related by parity check matrix instead of using lookup table method, which the whole to the power of k n code over matrix. This matrix, this makes the encoding decoding process simple and efficient. Now, you can define the minimum Hamming distance of the linear block. U as the minimum of Hamming distance between the two different code words. So, D minimum is called the minimum Hamming distance. Minimum Hamming distance. Here, the Hamming distance between two different code words, UI and UJ, is the number of bits having the different values, and can be found as the weight of the 1 or 2 sum or difference of the two codes. Suppose when the Hamming weight of the code word is defined as the number of non-zero bits, error detecting and correcting are defined to be the maximum number of detectable and correctable bit errors representatively, and they can be obtained from the minimum distance as follows. So there are two important parameters to calculate here, that is error detection correction now. So error detection correction process may called as reliability of the information. Error detection correction process may called as reliability of the information. So the error detection capability is equal to D minimum minus 1. D minimum minus 1. What is the D minimum? D minimum is called minimum Hamming distance. D minimum is minimum distance. D minimum minus 1 by 2. Okay. Now, these are the two important parameters in the linear block codes. So, students, please go to the textbook once. Linear block codes. Linear block codes can be represented with n comma k. So, n is the code word vectors, and k is the message vectors. There is parity bits are there. Parity bits are n minus k. Parity bits are there. N minus k is called p. Now that entire code word for the linear block code designed by U is equal to m into U is equal to m into g. U is equal to m into g. So where U is the code word vector, and m is message vector, and g is the generator matrix. If you multiply m into g, then you can design a code word U. M into g can design a code word U. So here the G is a very important matrix here. The matrix size of the G is equal to K into N. K into N. So K is 3. If N is equal to 7, 3 into 7 is the size of the matrix. Now for that linear block code, error detection capability is D minimum minus 1. Error correction capability is D minimum minus 1 by 2. Has to be calculated. Okay. Error detection capability, error correction capability called as reliability of the information. Okay. The next class go for generation of the matrix. So please pay attention to the next class. So it's very important concept for the encoding of the channel codes. Okay. So thank you for thank you.